In the previous lesson, we learned how to calculate for the changes of H, which is enthalpy, or the changes of G, or the changes of S, and they all have the same equation as the sum of the product minus the sum of reactants. Well, that is only when we have the overall chemical equation or reaction telling us that we have certain reactant produce product. Just like looking at this case right here. We have reactant producing this product. But the process of making this product right here from this reactant does not involve one single reaction, but rather it involves multiple reactions. Like 3 of these right here. 3 of these reactions are required to produce this overall chemical equation. And then each one of those has specific delta H. Now, how is that going to affect us in terms of the delta H reaction of that one? So basically, can you calculate for the delta H reaction of this one right here from the given data? Well, there is something called the Hess Law. Now, the Hess Law basically states that the overall enthalpy changes in a reaction, which is right here, delta H reaction, is the sum of all the reaction. Basically, the sum of all of this, you add all of them together for the process. So the process of this one take 3 reactions or require 3 separate reactions. You basically add all of them together, you will get your delta H of this one. Okay? Now here is the most important thing. This part right here. And that's the term independent. Well, independent means that does not depend on which order it will happen. This could happen first, this could happen first, and this could happen first, and this could happen last. So basically it's like this. Let's say you are hiking and you're going up here. It doesn't matter if you take this path like that, or you can take a straight path like this way. In the end, you still get there. Does that make sense? So you have your reactants over here, your reactants, okay? And this will be your product. So it doesn't matter which path you take, you still get your product in the end. And that's the beauty behind the Hess Law. You can manipulate this equation to get what you want. In order to use the Hess Law, there are 3 things that you need to look at. Pretty much 2 things, actually. That is, when you manipulate this equation, that is, if you reverse the equation, that means this product becomes reactant, you would do the same thing to the sign of delta H. Okay? If this is positive and you reverse it, it becomes negative. Then the other part is that if you multiply the reaction, that means you have to change the coefficient to match one of those. Now, if you multiply the reaction so that you can change the coefficient so that way it match with this overall, then you have to multiply the values of delta H by the same number. And lastly, you just combine all of them together with the new changes of delta H. So that's a lot of information, okay? And then the main strategy is always look at your overall equation and focus on the substances that are only written once in all the equation. And of course, in the process, you're going to write out the changes. So that way you can keep track of it. So let's do one problem together. From the data below, calculate delta H for the reaction. So basically calculate delta H of the reaction, okay? In this case, this is the reaction I'm referring to. Now you look at all these right here, and you're comparing to this. This is our final result. This is the overall. This is what we want to get by combining all of this together, okay? We realize that, look at carbon dioxide, okay? How many times do you see carbon dioxide written? It is only once here, isn't it? You only see carbon dioxide written once. And then carbon, how about carbon? You only see carbon written once as well. Let's circle that, how about that? Okay, but for oxygen, you see here and there. And what about water? Well, water is not in our thing, so we don't have to focus on it. So what do we want to focus on? Of course, let's start with whatever you see first, carbon dioxide, okay? Notice how I ignore oxygen, because you see oxygen in multiple places here. So for carbon dioxide, the overall only has one carbon dioxide. So I go over here, but look at this, I have two carbon dioxide. And this carbon dioxide, of course, is on the reactant side, and this is on the product side. So it's fine. So we don't have to flip the reaction because it's already on the same size already. But I have to make this so that it only have one carbon dioxide. So what do I have to do? Of course, I have to divide by 2, but another way of dividing by 2 in terms of multiplication is multiply by 1/2. So this will divide by 2, of course, and that will give us 1. And this will divide by 2 because we multiply by 1/2. And this same thing right here, oh, there's a little bit of space with it, that's fine, will be multiplied by 1. And then we have this one, 7/2 multiplied by 1/2. What's 7/2 times 1/2? Let's show the math. 7/2 times 1/2 give us 7/4. So we have 7/4 in that case, okay? In this case, we have to multiply whatever number to our delta H right here, which we will multiply by 1/2 as well. See how that works? Okay, so let's rewrite this so that way it has become less confusing for us. We have 1 CO2, and the state of matter is important as well, so we have to write that down. So we have 3 H2O liquid producing 1/2. Oh well, this 3/2 producing 1/2 C2H6 gases plus 7/4 O2. There you go. And this is gases as well. The state of matter is important as well. They have to be the same in order to cancel it out. So that's what we have right there. Okay. And of course we can do the math later for that part. The next part is carbon. Okay. And carbon is right here. Notice carbon is on the product side. So do I have to flip the side? No, because it's already on the same size as your overall. Now, what else do we need to do? Oh, look at this. We only have one carbon, but how many carbon do we have here? We have 2. So we do the same thing. We have to multiply the coefficient by 1/2. Okay? So if we do that, this will become, let me rewrite again, 1/2. Okay? C2H6 gases. And that produces, what is 1/2 times 2? Of course, it's 1 carbon in a solid. And then what's 3 multiplied 1/2? Of course, that is 3/2 of H2 in gaseous form. Isn't that easy? And of course, we had to multiply this by 1/2. Then what's the next thing we have to do? Now is the oxygen. Okay, so look at the oxygen. We have it here, and we have it there. But what about the water? Notice how the water is over here, and then there's water right here. But look at the overall reaction. Do you see any water at all? We cannot change or flip this one because this carbon dioxide has to be here, right? So what do we have to do? Well, of course, the only thing left we have to do is to bring that water on the other side so that we can cancel out, because this water on the reactant and this water on the reactant, they would never cancel out. They would add it together, right? So we are going to flip this. We're going to flip this over here. That's one thing. So let's do that. How about that? And if we flip it, what do we have? We have H2 gases plus 1/2 O2 gases producing our H2O liquid. Okay, and this is being multiplied by -1 because we flip it. Okay, now let's check our work. Do we have to do anything else? We know that carbon dioxide is over here, carbon is over there, that's good. The thing we have to realize is that, look at C2H6. Do you see any of them on the overall reaction? So they must cancel out. Do they really cancel out? Well, we have 1/2 of it right here and 1/2 of it on the product side. Of course, they cancel out. There you go. Now we cancel that one out. What else do we have? Okay, then we have 3/2 of water. And what else do we have? we have 1/2 of water. Ooh, that's very interesting. Okay, so what do we have to do? Notice how we have 3/2 of water here, and then we have 1 water here. So not only that we have to flip it, we actually have to multiply it by that 3/2 as well. And when we multiply this by 3/2, what is that going to be? That will give us 3/2 of H2. And what is 3/2 times 1/2 for this part right here? Okay, so 3/2 or 3/2 times 1/2 give us what? That's 3 times 1 give us 3. What's 2 times 2 give us 4. So now what we have here is going to be 3/4. Okay, see how that worked? And then what do we have? Of course, this is going to be 3/2 over 2. Okay, notice how I continue to apply patterns to cancel out. So now I can cancel out my water. Okay, which is good. The water cancel out. And the only thing that's left, oh, what about the hydrogen? Oh, well, the hydrogen here is 3/2. 3/2. So the hydrogen cancel out, that's good. And the only thing that's left is the oxygen. And we only want 1 oxygen. Here we have 3/4. Okay. And that is combining with 7/4. How does that work? Let's look at 3/4 minus 7/4. So here we have 3/4. Let's do a basic fraction. Hopefully you remember fraction. Okay. Minus, or other way around, so that way we avoid negative. Oh, well, just do negative. Doesn't really matter. 7/4. What is 3 minus 7? Of course, that is -4. And that is over 4. Give us what? -1. But it doesn't really matter, right? This negative is telling you that this is on the product side. So it doesn't really matter if you take 7/4 minus 3/4. That will still give us 4/4. We just need to realize that this leftover is on the product side because it's where it has more. So that give us, cancel that out, give us 4/4 oxygen, which is equal to 1. And there you go. Everything cancel out, giving us our 1 CO2, producing 1 carbon, and lastly 1 oxygen. And that is what we focus on. Which is the overall. After we combine all the equations and simplify them to the point that we get our overall reaction, the next step is adding all the new delta H. Well, of course, we can plug this into the calculator directly using parentheses. First of all, each set is going to be parentheses, okay? So parentheses, in this case, we have 643 times -1 times 3/2. So we can use the negative signs right there, okay? So just to let you see over here, negative sign of into 3, and it's a fraction, 2 times 643, that's 1 set. Then we add, remember, add all the delta H, we add them together. The next set is this number times 1/2, which is 0.5, so we can say that 0.5 times 190.6, okay? Notice how I don't have to rewrite the number if you know how to use parentheses right there. And then the last part is just add, of course, this number times 1/2, remember, we multiply by 1/2. So 1/2 is 0.5 times that number 3511.1, okay? And that gives us our answer of delta H reaction for this right here, equal to 866.35. And the unit is kilojoule. And that's our answer right there. Isn't that crazy? Whew. Now let's try another problem. Again, using the data from this 3 reaction to determine the delta H of reaction for this overall reaction right here. Okay, so keep that in mind. So this is what you see normally in regular chem. But in AP Chem, to do this process itself, from this reaction produce this product, is actually require 3 separate reactions. Now, does the order of event or reaction really important? No. based on the Hess law, it is independent of the result, okay? But the overall changes will always be the sum of product minus the sum of reactant. Of course, if we have the table, we can solve that directly by looking for each one of those, but we don't, and we are given an alternative. In this case, we go back to the rule and look at the same strategy, right? Focus on the substance that are written only once. Now, we look at this. Let's look at H2SO4. How many times do you see it's written in here? Oh, it's only once, right there. So we can circle that and we box that. We want to pay attention to it. How about SO3? How many times do you see it's written on here? Oh, it's also once. So let me circle that. How about water? Well, never mind. Water is everywhere. And they will also have H2S and O that are not on here. So we had to realize that it's being canceled out in the process. Again, starting with the first one that is unique to us. H2SO4, which is right here. Now look at this. This is on the reactant side, right? But over here is on the product side. So what do we have to do? Of course, we have to flip it. So that way, it's all on the reactant side. But look at the coefficient. Do we have the coefficient of 1 here and the coefficient of 1 there? So that's good. So all we have to do is just flip it, which we have to multiply by -1. Because based on the rules, when you reverse the reaction, you change the sign, which is the opposite of it. Now, let's reverse this reaction. We have H2SO4, and of course the state of matter is very important as well. The different state of matter, you cannot cancel them out. So this one is 2O2 gas form plus H2S in gas form. Okay, we are done with that part. Now let's look at SO3. SO3 is on the product side, which is right here as well. So do we have to make any changes to SO3? Well, we'll see. Now let's look at SO3. SO3 is on the product side, and it is on the product side here as well. So let's look at the coefficient. It's 1. It's 1. So do we have to make any changes? No. So that remains the same. So we can just box that out and say that remains the same. Oh, let me rewrite again. So that way we can see more clearly. H2S G plus 2O2. So that way we can cancel out easily, right? SO3 G plus H2O L, which is liquid. And we don't have to do anything to it. And lastly, we have water. Now, just look at this. Water is in a gas state. We also have water in liquid. We also have water in liquid, and we also have water in gas state. We only want to keep the gases one, okay? And the gases one is on the product side, which is good, right there. And we only want 1, and which is good. So, and this is the only equation left allow us to manipulate. Do we have to do anything to it? Well, in this case, I don't see anything that we have to do, okay? Because 1 water gas, 1 water gas. So it is done. So we just have H2O liquid producing H2O gas. Now let's see, does this really cancel out? Well, we can see that the liquid water cancel out that easily, and we can see the H2S gas cancel that out. What about the oxygen? That cancel out as well. I forgot to put a gas state there. Sorry about that. And does this really cancel out? We have our part right there. Boom, and voila. That's beautiful. Isn't that easy? Look at that. It looked complicated, but it's really easy if you take the time to write out all the work. So the overall change is really just this part right here, isn't it? So let's use our calculator and plug them in. Of course, we use parentheses and plug everything in. We have -1 times that negative answer, which is -235.5, parentheses to group that together, and we just add negative, okay, remember, don't use this minus sign as a negative, 207, add 44, and give us our answer of 1. So our delta H of reaction for this right here, okay, it's equal to 72.5 kilojoule. Isn't that easy? Beautiful. Voila. And that's all you have to do.